today we are going to discuss different types of equalizer, which is called adaptive equalizers, as part of your advanced communication system. That means in wireless propagation channel, how this multipath effect can be adaptively negated using adaptive equalizers. So this is the block diagram of a basic adaptive equalizer, which is also a type of linear equalizer only. So the received signal is actually your YK terms. So this is your received input signal here. Each of this received input signal is now delayed with respect to time, and every symbol is actually multiplied with a constant coefficient factor. What is the constant coefficient factor here? It is omega 0k for the current received symbol, omega 1k for the first delayed symbol, omega 2k or W2k for yk minus 2, and omega or wnk for yk minus n. Okay, so what is this k minus 1, k minus 2, k minus n? This is nothing but the previous symbol. So if I have explained this last day also, suppose you have a symbol train like this. Okay, so this is your actually multiple symbols transmitted here. So this is 1, this is 1, this is 1. So if I am currently transmitting, suppose currently transmitting this symbol, but I have already sent these two. So this is my YK, current symbol being transmitted. The exact one step is your YK minus 1. That means the previous one that is already being transmitted. It has already been sent. And this is YK minus 2. Okay. So why are we bothered with the previous symbol which has already been sent? We are bothered with this. Why? Because every symbol in your multipath effect is having overlapping because of ISI. So what is the overlapping? So this current symbol will be overlapping with the other symbol, and okay, sorry. So this would be actually, let me correct this. The correct symbol will be, this is YK, this is YK minus 1, and this is YK minus 2. I'm going reverse actually. Okay. So this is my actual correct sequence. So when I'm transmitting this symbol, first symbol, previous symbol, so this symbol is overlapping with the next symbol in line because of ISI. So what is the overlapping region? This is the overlapping region. This symbol, second symbol, will be overlapping with my current transmitted symbol. So what is my overlapping region? This is my overlapping region. Okay. So due to this ISI effect, the signals or symbols are delayed with respect to time. So when they are getting delayed, the previous transmitted signal is overlapping with the next symbol in line. Again, YK minus 1 is overlapping with YK in next symbol in the line. So like this, each of the previous symbol is now overlapping with the current symbol. That is why we are delaying each of the symbols here. That means each YK, YK minus 1, YK minus 2 and YK minus n are each of the symbols in the transmitted signal. Okay. So this is my first transmitted signal, this is the next, and this is the current one. And each of these factors is multiplied with a constant coefficient factors here. These coefficients are being generated using one algorithm. That algorithm is always calculating the current updated multiplication factor with respect to the old multiplication factor plus the correction term. If you remember that formula, this is my formula there. So what is the correction term here? So correction term means what? This is being updated every time. Previous value is updated with the correction, is added with the correction term, and you're generating the updated value. So this algorithm is actually changing the constant values here. Okay. Now, how is this correction term being created? So using the already known series. That means this is the training data. So using the training sequence, we already have known that what is the characteristics of the channel. Okay, based on that, we already know how the time varying nature of the channel is behaving, and based on that, we already know what would be the error behavior, and using this, we are generating the correction factor and we are updating the value of the multiplication factor. Clear? Now with this, when you are multiplying this constant factor with this each symbol, you are generating the output here, and each of this output at the receiver is added up. You are taking a summation of each of the output and you are generating the output at the equalizer, which is your regenerated transmitted signal. So what is my error factor cap E here? EK is nothing but the actual transmitted signal minus your regenerated output at the equalizer end. Okay. So this is your error signal here. So this process will continue until and unless this error signal is reducing in time. Okay. So what are we doing? We are always using the training data training sequence. We are generating this factor correction factor, updating the value of omega k or wk, multiplying it with the received signals, adding it up, regenerating the signal, and again calculating the value of error. If the value is going up, we are again repeating the same process again and again. So this is the basic working mechanism of an adaptive equalizer. This is a very simple working mechanism of the adaptive equalizer. So using this block diagram, you are able to explain how an adaptive equalizer is working in actual practical scenario. Okay. Now, in your adaptive equalizers, there are different kinds of algorithms. Like I've just discussed, algorithms are used to update the correction factor, to always change this multiplication factor as per the time varying nature of the channel. So what are the different types of algorithms that are used for adaptive equalizers? So first one is your least mean square adaptive equalizer algorithm. This is one of the most simplest kind of algorithms which is used for making the adaptive equalizer. Okay. In this case, this is very simple steps. The first step is what is the equalizer output? The equalizer output will have some weighting factor or omega k or wk factors or constant coefficients which are changing with respect to time as the channel characteristics are varying with respect to time. Okay. These are multiplied with the received signal yk. Now we are calculating the error factor here. What is the error factor? This is dk minus dk cap. Now, for this adaptive equalizer, we are utilizing this formula, which is very, very important formula here. The updated coefficient value is dependent on the previous or the old coefficient with respect to one term, which is mu ek into yk. What is this mu ek into yk? This mu ek into yk, this term is your correction term actually. Okay. So this term is nothing but your correction term actually. So in correction term, you are having three factors. What are the three factors? You have a mu factor which is called the step size. Step size means what is the gap or what is the difference. Step size means suppose you are taking a sample at 0, next sample will be at 0.1. Another sample would be at 0.2. So what is the gap actually? The gap is called the step size. In this case, this is 0.1. This is also 0.1. So, step size means between two different values, what is the gap? So, I am moving with a constant gap of 0.1. That means my next sample would be at 0.3. Okay. So, this is called the step size. So you can have step size as low as 0.001 like this. You can have constant step size. So mu can be very, very small or mu can be very, very large. Large means suppose I'm taking it as 10. So if my first sample is at 0, my next sample would be at 10. Then the next sample would be at 20. Then the next sample would be at 30. So what am I doing? I'm calculating the gap between the two, which is 10. So this is my step size. Okay. So this is called step size here. Now what is happening here? In this case, we are using one step size, we are using one error signal. So the error signal here EK is actually your, so the error signal EK is also there in your correction term, and your received signal vector is also there in the correction term. Okay. So correction term has three factors. It has step size, it has error, it has received signal factor. Now any change in the error will cause to change the step size. So if error is more, then the step size will be more. If error is less, then the step size will be less. Like that, you will keep on changing the correction factor and you will calculate new weights or new coefficients, and with this new weight you will update the value and you will regenerate the signal here, and then you will calculate the error here and then repeat the process. So this is how adaptive equalizers, in this case least mean square adaptive equalizers or LMS equalizer, is working. Okay. So equalizer checks the error, and if there is a slight change in the weights, it will try to reduce the error. So this is the basic working mechanism of adaptive equalizers in case of LMS algorithm. Okay. So LMS algorithm has two scenarios or two case studies. One is based on the size of the step. So if the size of the step is very, very small, then we are doing precise control. Precise means we are doing step by step. We are checking the channel characteristics, time varying channel characteristics in very small steps. So I'm checking in very small steps means I'm checking precisely. I'm checking in very, very minutely. Okay. So very minute checking means what? It is going to take a lot of amount of time. So more time means what? It is going to take, the process is very, very slow. So equalizer is sensing the channel in very small steps. Small steps means it is going to take more amount of time. More amount of time means it is actually going very, very slow. So very, very slow means it will take more amount of time to actually reduce the error. So reducing the error means it is slow convergence. Okay. And another case can be, so this is case 1. So this is your first scenario. Second scenario is when the size of the step is very, very large, then what will happen? So if it is very large, that means the equalizer output sometimes it becomes unstable. Why? Because we are taking larger step size. So error margin will always be changing with a wide margin. So error is changing. That means it is always either going very high or very low. So does not properly converge with respect to time. So this becomes fast, but it becomes unstable also. So your step size should always be chosen very, very carefully. For precise or small errors, we should always, or slowly changing channel, we should always use a very small value of the step size. For fast changing channel, so precise means for slow changing channel. If the channel is changing very slowly, you should use a very small value of step size. If the channel is changing fast, so fast means there is very fast change in the channel characteristics, then use a large value of step size so that you can also reduce the error fast. So what are the basic working flow or steps involved in an LMS adaptive equalizer? So first step is you receive the symbol, that means all different types of symbols, that is yk, yk minus 1, yk minus 2, all the symbols are received at the receiver side. Now what is the equalizer doing at the receiver side? The equalizer will calculate the value of weighting coefficient, multiply this with the received signal and generate the output of the receiver at the receiver, which is called DK cap. In the third step, it will try to compare the decision of this regenerated output, and it will try to see what is the error factor. Okay. So what is the error factor means? It will try to calculate the difference between the actual transmitted signal and the received signal or the equalizer output. Now it will try to minimize this error using an algorithm which is called the least mean square algorithm, and it will try to calibrate the coefficients. It will try to update the value of the coefficient using the value of step size. So if error is large, step size will be large. If error is small, step size will be small. So how are we doing this? If error is small, you use a small step size. If error is large, you use a large value of mu or step size. Based on this, convergence will be slow or fast, and we can reduce the amount of error. Until that, we have to keep on repeating the same process for all other symbols in the transmission. Okay. Now there is one more adaptive equalizer in your syllabus, which is called RLS adaptive equalizer. In this case, RLS means recursive least square adaptive equalizer. This is one more algorithm basically. So in this case, recursive means what? Recursive means you're doing one process repeatedly, continuously, always. Okay. So adaptive equalizers with RLS mechanism or algorithm, they are continuously updating the value of the weight in order to reduce the ISI for the time varying channel. So continuously means recursively, always. They are always updating the value fast. Okay. So what is the difference of RLS with LMS? LMS is slow, but RLS is much faster. Okay, why is it faster? Because it is always changing the value of this multiplication factor. So if I compare the LMS with the RLS, what is the major differences? LMS means least mean square error values, and RLS is recursive least square algorithm. Now, in terms of complexity, LMS is lower in complexity because it does not do much change. It is using a constant step size factor. If it is small, slowly changing, it will use a small size of mu. So the step factor is the only factor that is being used here. RLS, the complexity is higher. Okay. Why higher? We will study this in the next slide. Convergence is much slower for your LMS because it is choosing a small value of step size. So it will take more number of steps. More number of steps means it is going to take more amount of time. Okay. RLS compared to LMS is much more faster. The implementation of LMS is simple. Why? Because in this case, it is having lower complexity means it is easier to implement. Higher complexity means it is more complex to or difficult to implement. Now it is suitable for what? It is suitable for slowly changing channels. Slowly changing channels, if you use the value of mu very, very small, then you can actually do precise tracking of the channel and you can actually overcome the error very precisely. But it will take larger amount of time, or it will take a long time and very slow process. Okay. But RLS is used for fast changing channel. Why? Because it will do it very fast. And if there is very fast change in the channel characteristics, then you have to track the fast changing nature of the channel. So you don't have much time to waste. So you have to do this faster. So LMS is not useful for fast changing channel. Why? Because it is very, very slow and time taking. But RLS is much more faster and we are going to do this faster. So RLS is much preferred compared to your LMS. Why? Because for fast changing channel, you have to study the channel fast. So if you want to study the channel fast, you can't waste time by doing precise tracking of the channel. So LMS is not used there. RLS is more preferred compared to your LMS for fast changing channel. Okay. So next, what is the steps of RLS adaptive equalizers? The steps are very, very simple. 1, 2, 3 steps are there and it is almost equal to your LMS, but the main differences I have pointed out here in this slide. So LMS basically it calculates the error of the current symbol. Current symbol means suppose I am using a symbol and transmitting the symbol YK. So for this, what is the error symbol? EK. That is what is LMS concerned about. Okay. But what is RLS doing? RLS will study all the previous channel, all the previous symbol error. Previous symbol means for YK minus 1, what was the previous error? The previous error was EK minus 1. For YK minus 2, what was the previous error? The previous error was EK minus 2. For YK minus 3, what was the previous error? The previous error was EK minus 3. So like this, all the previous errors that are there, they are actually studied and taken into consideration for RLS equalizer. Okay. So for RLS equalizer, we actually utilize all the previous errors in this case. How are we taking this into consideration? It uses this formula. What is the formula here? It is calculating the weighting factor based upon the square of the error, the mean square value of the error multiplied by some factor, lambda. What is this factor? The factor is called the forgetting factor. Okay. Now, what is this forgetting factor basically? The value of this lambda lies between 0 and 1. So, the value of lambda is between 0 and 1. So, when it is equal to 1, all the past errors are treated equally. Equally means all the value of EK minus 1, EK minus 2, EK minus 3, every value is equal to one fixed value. Suppose what is the fixed value? Suppose it is 1. That means EK minus 1 is also 1, EK minus 2 is also 1, EK minus 3 is also 1. That means they are all same and they are treated equally. Okay. But when the value of the lambda is less than 1, that means the recent errors are given more importance compared to the older errors. So if I compare the errors in this case, so let me just remove this now. So if I compare the recent errors in this case, let me take one different color. Recent error means EK minus 1 is the recent error compared to your EK minus 2 and EK minus 3. These are old errors. So when the value of lambda is less than 1, then it will give more importance to the current or recent errors. So current is EK, recent is EK minus 1, but old is EK minus 2 and EK minus 3. So all these old errors will not be taken into consideration, but the recent errors will be taken into consideration. So what are we doing? We are tracking all the previous errors with the recent errors, and we are trying to understand the nature of the channel based on the previous error values also. This is the main difference between RLS adaptive equalizer and LMS adaptive equalizer algorithm. So this is the main. In LMS, what are we doing? In LMS, we are using only one error factor, EK. So one error factor for current symbol. So currently we are transmitting YK. So this is the current error factor. But RLS uses all the previous error factors for each of the previous transmitted symbol. So all previous data, past data is also used here to understand the nature of the channel better. Okay, that is why this is more faster compared to LMS. But because I need all the previous error factors, this becomes more complex because I'm studying all the previous error factors here. So more complex means it is difficult to implement, but it is much faster for fast varying channel. Now, the performance parameters of adaptive algorithms are dependent on certain parameters here. This is the main limiting or main important parameters for judging how one algorithm is better than the other algorithm. So first parameter always is the rate of convergence. Rate of convergence means how fast the equalizer can understand the channel and can minimize the value of error. This is called convergence. So equalizer will understand the channel, will try to minimize the value of error by choosing the value of constant factors Wk. So the faster it updates the value of Wk and it will minimize the error, it is optimum, best solution. Okay. So fast convergence means fast channel, it is able to track, it is able to update the Wk value, and it is able to minimize the error fast. So this is called the rate of convergence. Misadjustment. Misadjustment means suppose my ideal solution is given and my practical solution is different from the ideal solution. So what is the difference between the ideal and the practical solution? Ideal means optimum solution, which may not be possible in practical scenario. So what is the practical solution? And the difference between the two is called the misjudgment. So the lower amount of misjudgment, the better is the performance of the equalizer. That means the ideal and the practical solution should be as close to each other as possible. Okay. Next comes your computational complexity. Complexity increases if you have more number of iterations. Iterations means if you have to do it more number of times. Update the value of the Wk or omega k more number of times. So lower the complexity, better is the implementation, means easier implementation. Easier implementation, it is much more cheaper in hardware, etc. So this is much better in terms of practical scenario. Numerical properties like certain mathematical properties like round off errors, finite word length, representation errors. So these are all numerical, means mathematical errors. Lower the mathematical errors, better is the performance of the algorithm. So this is what is there for your adaptive algorithm, adaptive equalizer as part of your linear equalizers. Okay. So if I want to conclude today, so we have discussed until now in all the previous lectures what is equalizer, what is the need of equalizer, how equalizer minimizes ISI, how equalizer increases the noise present in the wireless communication channel, what are the types of equalizers. We have discussed zero forcing equalizer as your linear equalizer sample, and we have also discussed minimum mean square error equalizer as part of your linear equalizer, and we have compared the performance of both of them, and we have found that MMSE is much better compared to zero forcing in terms of reducing both ISI and is your noise. Okay. We have also discussed adaptive equalizers, all the different types of adaptive equalizers. Adaptive equalizers are different compared to your linear equalizers, which are zero forcing and MMSE. How? Adaptive equalizers are always changing with respect to the changing nature of the channel. We have studied here two types of adaptive equalizer algorithms. One is called LMS or least mean square, and the other one is called RLS. In this RLS, we have studied recursive least mean square errors, least mean square algorithm. Recursive means it is always calculating again and again based on all the previous data or based on all the previous error values. So all previous error values are studied in RLS. That is why this is more advantageous for fast changing channel, and LMS is doing precise calculation. So this is used for slow changing channel. So time varying nature, we have studied two types. If it is slowly varying, then we should use LMS. If it is fast varying channel, then we should use RLS adaptive equalizer. We have also studied the block diagram of adaptive equalizers. So everything is covered. We are only left in my next lecture. We will cover the only two topics that are left. That is non-linear equalizers, how linear and non-linear equalizers are different. And in this non-linear equalizer, you have two different categories. One is called decision feedback, and the other one is called maximum likelihood sequence estimation equalizer. So these two are the only factors topics which is left for discussion. So in our next lecture, we are going to discuss this. This is all for today.